All right, y'all. This week we're going to be talking about FRQs that have to do with rate and accumulation. Now, just kind of one thing you're not going to love this, but no two FRQs are really exactly alike. So, as we go through these next couple of weeks, I'm going to try and pull groups of FRQs that are pretty similar and that focus on the things that y'all are really saying that you're struggling with. But like I said, no two FRQs are exactly alike. It's going to be very difficult for me to find FRQs that follow the exact same steps. So even though I'm going to go over a bunch of things in this FRQ, some of the FRQs you see this week will have, a piece here or a piece there that's not covered in this one, just because they just aren't alike. But anyways, that being said, we're going to be looking at rate and accumulation. So rate and accumulation is going to be working with a lot where you're given a function that represents a rate, and you're going to be asked to integrate and derive off that function and kind of work in both directions. And we're going to talk about how we know which one to do, what kind of keywords to look for, that sort of stuff. Okay. So on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G of t is equal to 90 plus 45 cosine of t squared over 18, where t is measured in hours and 0 is less than or equal to t is less than or equal to 8. At the beginning of the workday, t equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation, 0 is less than or equal to t, which is less than or equal to 8. The plant processes gravel at a constant rate of 100 tons per hour. All right, first and foremost, we want to find g prime of 5 using correct units. Interpret your answer in the context of this problem. All right, so we have g prime of 5, we have g. We want to find g prime. So this is a calculator question, which means you can do this rather quickly in your calculator, but I'm going to show you how to do it by hand anyways. So if I wanted to find g prime, so I have to take g of t and I have to take my derivative. So part A, g of t is equal to 90 plus 45 cosine of t squared over 18. So our g prime, 90 is going to go away, 45 stays the same, cosine becomes negative sine, so negative 45 sine. Everything on the inside stays the same because this is our chain rule, so that chocolate stays untouched, times 2t, and then still over 18. All right. So from here, I can just plug in 5 to get g prime of 5, which, go to our calculator, clear out all that mess. So g prime of 5 is negative 45 sine alpha y equals t squared, so 5 squared over 18 times alpha y equals again, and we have 2 times 5 over 18. All right, and we get negative 24.587, which we can round off to negative 24.588. And just to show y'all that you can also do this all the way from scratch. You didn't even have to find the derivative in a calculator. So if I take my original equation, the 90 plus 45 cosine, I can go to math. And then you see option 8, that inderiv, that stands for function derivative. So d dx of 90 plus 45 cosine alpha y equals x squared over 18. And I want to evaluate it at x equals 5. And it gives us the same thing. So you can also have your calculator do this all for you from scratch. Okay, just want to show you both ways so you know if this is a non-calculator question, you can still do it. Okay, now let's talk about units. So we found the derivative. Okay, so what does g of t actually represent? So g of t is the rate at which unprocessed gravel arrives at a gravel processing plant. Okay, so g of t is already a rate. So since we found the derivative of g of t, we found the rate of the rate. So kind of think about it as the acceleration. We found essentially the second derivative. Okay, so negative 24.588 would be the rate at which gravel is arriving slow internet. So the rate at which gravel is arriving is decreasing at t is equal to 5 hours. So kind of to put that in perspective, that would essentially be negative 24.588 tons per hour squared, because it's an acceleration. Okay. So that is part A. So just kind of as a recap for part A, we knew to take the derivative because it asked for g prime, and we had g, so I had to take a derivative to get to there. Okay. The second piece, I knew it was the rate of a rate because I read back for what did it actually tell us g of t was. G of t is the rate at which unprocessed gravel arrives. So if I found the derivative of that, it's the rate of a rate. So it's that going from, remember we have our position, which is our original function, velocity, which is the first derivative, and then acceleration, which is the second derivative. So they gave us the velocity, that first derivative. We found the second derivative, even though we technically found g prime. Okay. So that's how I knew it was the rate of the rate. So because it's negative, it means it's decreasing. All right, part B. Find the total amount of unprocessed gravel that arrives at the plant during the hours of operation in this workday. So total amount that arrives is going to be from 0 to 8. Okay. Now, I just want the total amount. I don't care about how much is there already. I don't want to know how much is there at the end of the time. I just want to know the total amount that arrives. Okay. So if I'm going to an amount, right now I have the rate, okay, which is our velocity equation. I want to know the amount, which is kind of like our position equation. So how do I go from velocity to position? I have to integrate. So for part B, we want to take the integral from 0 to 8 because that's our whole workday of g of t dt. Okay, now in this case, this is a calculator question. I'm not going to be doing that by hand. If I did need to do that by hand, I would integrate and, plug everything in. But this one's calculator, so we can just type it into the calculator. So going back to our calculator, if it will ever get there. Sometimes my computer does not cooperate. There we go. All right, so math, integral 0 to 8. And then our function is 90 plus 45 cosine alpha y equals x squared over 18 dx. And we get 825.551. And then as always, we want to make sure that we include our units because this is a real world problem. So it would be in tons. Oh, you are being slow today. All right, so just as a recap on part B, how did I know to integrate? Because I had a function representing the rate that the gravel was arriving, and I wanted to know the total amount. So I had the velocity representative equation, and I wanted to find the position, so I had to integrate to go backwards. All right, part C. Is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5 hours? Show the work that leads to your answer. All right, so this one's a little confusing because we kind of talked about this already in part A where we found the derivative. And the derivative was the rate of the rate of the unprocessed gravel arriving. But that specifically was about just the gravel arriving. So in this plan, as they've told us, the unprocessed gravel is arriving from hour 0 to hour 8. And at the same time, during the hours of operation, 100 tons are processed each hour. Okay, and that's constant. We're always processing 100. So the amount coming in is changing. The amount being processed is not changing. It's always the same. Okay, so we want to compare those two things to each other. Okay, so we already know the rate that it's being processed at time equals 5. It's going to be that 100. But now I need to know the rate it's being processed, or the rate it's arriving at time equals 5. So what's my equation for the rate? Well, it's g of t. It's what we already have. So I'm going to plug in 5 and find g of 5. Man, sorry, y'all. This is a slow computer day. So g of 5. So going back to my calculator, because I'm not going to be able to plug that in without it. So 90 plus 45 cosine alpha y equals 5 squared over 18. And we get 98.141. Okay, so we're going to compare that. So that's the rate that gravel is arriving at hour 5. The rate that it's being processed is 100 tons per hour. So is the amount of unprocessed gravel at the plant increasing or decreasing at time equals 5? Okay, so it is decreasing. And that would be because g of 5, which equals 98.141, is less than 100, the rate of gravel being processed. Okay, so because the value of gravel coming in was less than the value of gravel being processed, the amount of gravel actually in the plant is going to be decreasing. Okay, so we're comparing the two rates to each other because the rate that was processing it was higher than the rate that was bringing it in. The overall amount would be decreasing. Okay, so now moving on to our very last question, part D. If my computer will load, there we go. All right, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? And then we want to justify our answer. All right, so we've talked about this before. We saw it in the mock exam. Anytime we talk about maxima, okay, if I want to know the maximum of an amount, I get maxes and mins from my first derivative. Now, I already have the first derivative. G of t, remember, represents that rate. So G of t is that first derivative. Okay, but I need to know the total amount. So unfortunately, to know the total, I have to also include how much was already there. So this is that accumulation piece. We're accumulating a certain amount of gravel over time. Okay, so at t equals 0, the plant has 500 tons of unprocessed gravel. So I'm going to have to include that 500 in anything that I do. So as I include that, I also need to include the rate that the gravel is coming in, so that G of t, and I need to include the rate that gravel is being taken out. Okay, so to kind of get an idea of just how much gravel there is at any point in time on the workday, which is a little bit different than B, because B was just asking how much arrived. D is now asking how much is there at any point in time. So we have to account for how much is arriving, how much is leaving, and how much was there at the beginning of the day. We have to kind of account for everything. Okay, so for part D, the first thing we really want to write is we want to write a new equation to represent our everything. Oop, why are you not writing? There we go. Sorry, y'all. It is a slow day here for my Cami. So for part D, we want, I'm going to call it E for everything. Okay, so my E of t, my function that represents everything that's in the plant, I have to include the 500. Okay, I have to include the 500. then I have to include the total amount, but I have to include the total considering what's coming in and what's being processed. So it's going to be the integral from 0 to t, okay, of g of t, which is the amount coming in, minus 100, which is the amount that's leaving. Okay, so does that kind of make sense that I'm taking into account 500, which is the amount that's there at the start of the day, and then I'm going to be adding to it the area under the curve, or the amount, accounting for both gravel coming in and gravel being processed. So that's going to be changing the amount that's in the plan at any point in time. Okay, so this is our function that represents the amount in gravel at any point in time. Okay, so now I need to talk about maximums. So maximums occur, as we said earlier, at endpoints. So we could have the most amount of gravel in the day could have been at the beginning at time 0. It could be at the end. It could be at time 8 that we are getting more gravel during the day as the day goes on. Or it could be at any relative maxes or mins that occur during the day. We don't exactly know what this function looks like. It could kind of be sloping up and then sloping back down. Okay, or it could kind of be going all sorts of wonky. We don't really know. Okay, but we do know that those relative maxes occur when the first derivative is equal to 0 and we switch from positive to negative. Okay, so what do we need to do? We need to derive our function. So e prime of t will be equal to, that 500 is going to go away, and then the derivative of the integral is just the function that we have inside. So g of t minus 100. So I'm going to take that function and I'm going to set it equal to 0. My computer is making me feel some sort of way today. So I'm going to set it equal to 0. So then we can go to our calculator. Remember, if we didn't have a calculator, they'd have it give us a function that was easy enough to solve this without it. There we go. So y equals, we have 90 plus 45 cosine of t squared, squared. I'm sorry, everyone. There we go, of t squared over 18. And then we want to subtract the 100. And I don't have to put parentheses around 100 because it's just 100. And then I want to know when this function is equal to 0. So I'm just going to set my y2 as equal to 0. So then we can graph. My window obviously was not edited from the last time we've been working with this. So 0 to 8. So I can get that whole picture. There we go. Okay, so we only have one spot where we're crossing 0. We are going from positive to negative, so it is a maximum. So let's go to second calculate, option 5 to find that intersection point. Enter, 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 and we get 4.92348. So t is equal to 4.92348. And 5 is usually a pretty safe bet of where to cut it off before you get to your final answer, to make sure your final answer is still within 3 decimal places. Okay, so now we need to consider the 3 points that we've talked about. We talked about 0, we've talked about 8, and we've talked about our relative max, which is 4.92348. So I'm going to find gosh. E of 0. E of 5. Not 5. E of 4.92. And E of 8. All right, so E of 0. Well, we already know how much was there at time equals 0. It's at 500. So we can just kind of ignore the rest of our function and just plug it straight in. All right, E of 4.92348. Remember, we're plugging it into this equation, this 500 plus 0 to 8, g of t minus 100 dt. Okay, now for time's sake, because this video has gone a little long, I'm just going to give you all what it is. So it should be 633.376. And then last but not least, E of 8, same idea. We'd be plugging 8 into our integral. So 500 plus the integral from 0 to 8, and that would give us 525 plus, or point, sorry. Why are you so slow? .551. All right, so we have 3 different amounts. We have the 500, we have the 633, and we have the 525. So which one's clearly the biggest? Well, it's that 4.92348. So the maximum value is 633.376 tons. And it does say to justify. So, for your justification, you could say anything of, the maximum considering the endpoints. It is E of whatever is greater than E of 0 and E of 8. What we know about the derivative, all sorts of those kind of things. You can really use just about anything as long as it is sound calculus to justify this. But that should be our answer. So just as a recap of everything we went over. So part A, they asked us to find G prime of 5. So we just derived and then plugged in 5. Nice and straightforward. Part B, they want us to find the total amount of unprocessed gravel that arrives. So we only use the equation for gravel arriving. And because we wanted to find the amount, not a rate, we integrated instead of derived. So we integrated because we wanted to find an amount. We wanted to go backwards. And we wanted for the entire day. So we did the integral from 0 to 8. Then part C, is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5? My gosh, this computer is driving me insane. There we go. All right. So is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5? So now since we wanted to find out if the rate is increasing or decreasing, consider both. And then we compared those two to each other. So we got 98.141, and then the rate of it being processed was 100. Since the rate of it arriving was less than the rate of it being processed, the rate of gravel was decreasing, which when we go back to our calculator where we actually put those two equations in together, we can see that if our maximum of the amount in the plant being at 4.92, does it make sense that it does go down over time? Yeah, of course, because as we get past that, as we get into the 5s, our equation goes under. Our equation is negative, so it is decreasing over time. Okay, and then last but not least, part D, it was the doozy. So we had to find the maximum amount. So we had to consider everything that was happening. We had to consider the amount of gravel that was there when the day started, which was the 500 tons. And then because we wanted to find the actual amount, we had to integrate, but we had to integrate both functions, the rate of it coming in and the rate of it being processed. So we did that G of T minus the 100, G of T being it coming in, 100 being it being processed. So then we found the derivative of that because I needed to find a maximum. So I needed to see if there's any relative maxes or mins, which we found one by setting it equal to 0. And then I actually evaluated E of 0 and E of 8, which were the endpoints, and E of that relative max by plugging it into our function for E. And then whichever one was the biggest, that was the one that turned out to be our maximum of the day, which was the 633. All right. All right, y'all. Sorry this is getting out so late. Just didn't want to test the technology too much more this week with all of our issues at the beginning of the week. So I'm going to be going over the self-assessment FRQs, the two from last week with rate and accumulation. So starting with our 2016, we have water being pumped into a tank at a rate modeled by W of T is equal to 2000 E to the negative T squared over 20 liters per hour from 0 to 8. Where T is measured in hours, water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing from 0 to 8. And then they give us some selected values of R of T up above. At time T equals 0, there are 50,000 liters of water in the tank. So that's our initial condition. W is representing water going in, and they give us a nice easy equation to work with. R is the rate of water going out, and they give us a not so easy, but still not too hard table of values to work with. Both W of T and R of T are rates, so they are that first derivative that they're representing. So let's talk about A. We want to estimate R prime of 2. So we want to estimate the rate of water being removed. So if I want to estimate, remember, anytime they ask us to estimate the derivative, what are we going to do? We want to do that AROC, that average rate of change. So for part A, R prime of 2 is equal to, we want to estimate 2, so we want to pick values on either side of 2, so 3 and 1. So R of 3 minus R of 1 over 3 minus 1. So R of 3 is 950, so 950 minus 1190 over 2. And that gives us did I do that wrong? 1190. Negative 120. So negative 120. And then it's the rate of the rate. So the rate of R of T. R of T is measured in liters per hour. So the rate, R prime of T, would be liters per hour squared. It's that acceleration value. Okay, so that's part A. Part B, we want to use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. And then as a second spot, is this an overestimate or underestimate of the total amount of water removed, and give a reason. Okay, so first off is a Riemann sum. Riemann sums are pretty straightforward. Okay, it is a left Riemann sum, which means I'm going to be using these subintervals. I'm going to be multiplying them by the leftmost value for each of the intervals. So 1 times 1340 plus, let's see, 2 times 1190 plus 3 times 950 plus 2 times 740. Remember, this is estimating the area under the curve, so this is estimating, if this helps out. the integral from 0 to 8 of r of t. And use our squiggly equal signs to show that it's just an estimation. Okay, so then type all that into our calculator. So 1 times 1340, that's just 1340. So 1340 plus 2 times 1190 plus 3 times 940, I believe. Yep. No, 950. Is it 950? It is 950. Plus 2 times 740. There's where that 40 was coming from. And that gives us 8,050. And now, once again, talking about units. So we did the integral of r of t. R of t is liters per hour. The derivative of r of t is liters per hour squared, which means the integral of r of t, we're going from velocity, our first derivative, to our original function. So it's just going to be an amount. So this should just be liters. Okay, now the second part of part B is they want us to talk about whether this is an overestimate of the value of liters removed or an underestimate of the value of liters removed. So remember, when we first talked about Riemann sums, talking about if it's an overestimate or underestimate, it depended on the shape of the function. So our function, our r of t, is decreasing over time. It's going down. So we have a function going like this. All right, this is r of t. So if I'm doing my little Riemann sum, my left-hand Riemann sum, as I draw those leftmost rectangles, you can probably see that my rectangles are going to be up above the curve because it's decreasing over time. So because it's a decreasing function, my left rectangles are going to be up above the curve. So that would be an underestimate. So it is an underestimate. And we would say because r of t is decreasing. On 0 is less than or equal to t is less than or equal to 8. So the whole time, curve is decreasing. All right. That takes us through part B. Part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so now we're talking about the whole tank. So we want to know how much water is in the tank at the beginning at time t equals 0, and how much water is in the tank at the end. So how much water is going into the tank and how much water is being taken out of the tank. So now we're going to include both r of t and w of t. So this is our big integral equation that we've kind of been talking about on all of these. So for part C, we have our initial condition. So our initial condition is 50,000 liters of water in the tank. So 50,000. Let's call this, I don't want to use T. We'll say V for volume of the tank. So V of T is equal to 50,000 plus, now we're going to do the integral of both of our equations because we want to find that amount of water. So plus 0 to 8 for our time. And then it is, which one is representing water pumping in? W of T is pumping in, so W of T minus, so I'm not going to minus R of T because R of T isn't actually a function. R of T is a table of values. But we did already find the amount of water removed, or our estimate. They even tell us in part C, use your answer from part B. So instead, I'm just going to minus 8,050. And I'm not integrating 8,050 because that's already an amount in liters. So 50,000 is an amount in liters. 8,050 is an amount of liters. The only thing that's not an amount in liters is W of T because that's liters per hour. So I need to integrate W of T to get the amount of liters that comes into the tank. And that's going to be my answer. So go in here. I hit math, then option 9. So math 9, we're going from 0 to 8. Before that, I can add in my 50,000. So 50,000 less the integral from 0 to 8 of w of t, which is this big old mess, 2,000 e to the negative t squared over 20. So 2,000 second e to, is it negative t squared? Yep, negative t squared 20 dt. And then I want to add 8,050, that estimate we found in part B. We get 65,886. Just checking, making sure I didn't lead you astray. What did I do wrong? Oh, I added my 8,050. My bad. We're subtracting the 8,050. Like, duh. There we go. 49,786.195. We always want to round to that 3 decimal places, unless it tells us to do it to a whole number. Let's see. Nope. So 49,786. .195, and then liters, because that is an amount in liters because we integrated. All right, now the last part for part D. Is there a time t where the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? And explain why or why not. Okay, so we want to know, is there a time where the rates are the same? So really what I want to know is there a time where what we really want to prove is that W of t and R of t are equal to the same value. Now, it's a little hard to consider, find what that value is going to be equal and then compare, because, there's literally any value that they're equal to. But if W of t and R of t are equal to each other, then W of t minus R of t should equal what? They should equal 0 because they're the exact same value. So we can kind of account for all those values if we consider W of t minus R of t. Now, how can I prove that at some point W of t minus R of t is equal to 0? Well, to prove that, I just need to use my intermediate value theorem. Intermediate value theorem is how I prove that a value exists on some interval. And the interval I'm trying to prove that it exists on is between 0 and 8. So to prove that W of t minus R of t equals 0 at some time between 0 and 8, I have to know what's happening on the endpoint. So I have to know what's happening at W of t minus R of t at 0 and at W of t minus R of t at 8. So let's first find W of t, or W of 0 minus R of 0. So W of 0 minus R of 0. W of 0, if I plugged 0 into this equation here, that would be e to the 0, which is just 1. 1 times 2,000 is 2,000. So that would be 2,000 minus 1340 for R of t. I'm getting that from the table, which is equal to 660. Okay. And I'm not really worried about units at this moment in time because my answer is not really going to be my units. Then the other one I want to find is W of 8 minus R of 8. All right, and this one I'm going to have to plug in because I don't know what that to the 8 is. So 2,000 e to the negative 8 squared, I believe. Yep, negative 8 squared divided by 20. Divided by 20, not minus 20. And just to make sure everything's accounted for correctly, let's make sure we put that 8 in some parentheses. And we'll be a little extra cautious and add some parentheses here. Ooh. All right, so we get 81.524. And then I am subtracting 700, which I don't really need to know exactly what that is, but it's about negative 620. We can be rough because it doesn't have to be perfect. All right. So at W of 0 minus R of 0, I got positive 660. At W of 8 minus R of 8, I got negative 620. So I'm going from positive to negative. So from 0 to 8, I have to go from a positive value down to a negative value. At some point, does W of t minus R of t have to equal 0? Yes, that's what IVT says. So as a conclusion, we want to make sure we talk about all the things for IVT. So first of all, function has to be continuous. Up here, differentiable, which implies continuity. They don't tell us about W of t, but it's a function involving E. E is continuous for all x values. It just goes a nice big swoop. So they don't really need to tell us that. We should be good. So we'll say that W of t minus R of t is continuous on 0 to 8. Close interval. So 0 to 8. And W of 0 minus R of 0 is greater than 0. And W of 8 minus R of 8 is less than 0. So we have function is continuous. At 0, we're positive. At 8, we're negative. Therefore, W of t minus R of t equals 0 at some t on 0 to 8. Open interval. Hey, and that's basically just quoting IVT to a t. Nice short little sum up sentence. Okay, so to kind of recap what we did for everything for our first question, for part A, we needed to estimate R prime of 2. Since we were estimating the derivative, we applied our average rate of change, our f of b minus f of a over b minus a. We chose 3 and 1 because 2 is in between 3 and 1. For part B, we wanted to use a left Riemann sum using the subintervals indicated by the table. So we made the 4 subintervals indicated in the table, and we multiplied by the left value for a left Riemann sum. Then once we found that, they asked us to determine if it's an over or underestimate. We determined it's an underestimate because our function R of t is decreasing in values. It goes from 1340 down to 700. So it's decreasing the whole time, which means our left little rectangles are going to be above, which means it's, oh, why did I write underestimate? I'm crazy. Overestimate. Sorry. Sometimes. Overestimate. Sometimes I'm crazy. Ignore what I said earlier. It's an overestimate because R of t is decreasing. As you can clearly see that the rectangles are up above the curve. Ignore what I said earlier. All right. For part C, V of t is equal to 50,000. We are trying to estimate the total amount of water in the tank. So we accounted for the original amount of water in the tank, which was 50,000 at time 0. We added the integral of the rate of water entering, which was going to give us the amount of water that goes into the tank over those 8 hours. And then we took away our estimate for the amount of water that is being pumped out. Because we want to take away all the water that's leaving. So 50,000 liters, the integral of this is going to be some amount of liters, and then minus 8,050 liters gave us 49,786 liters after 8 hours. So that's our big kind of mega equation. Then last but not least, for part D, they wanted us to find a time when the rate water is going in is equal to the rate water going out. So the only way we could really account for all those possibilities is by finding when W of t minus R of t is equal to 0, because if WT minus R of T is equal to 0, then that means the rate of water going in and the rate of water going out is the same number. So then to prove that that was equal to 0, we used IVT because IVT proves that values on the original function are in between two values. So we plugged in at our endpoints. And since we had a sign change of going from positive to negative, that means our curve has to go through 0, which means W of t minus R of t has to equal 0 at some point on 0 to 8, which means W of t has to be equal to R of t at some point on 0 to 8. Okay, so if you want to pause right now, that's the first one. Take a break, and I'm going to go straight into the second question. All right, y'all, we're going to be talking about the 2015 question number 1. The rate at which rainwater flows into a drain pipe is modeled by the function R, where R of t is equal to 20 sine of t squared over 35 in cubic feet per hour. T is measured in hours, and the interval is 0 to 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of t is equal to negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour, for 0 is less than or equal to t is less than or equal to 8. There are 30 cubic feet of water in the pipe at time t equals 0. At this point, you're probably wondering why calculus teachers are so concerned about rainwater flowing through drain pipes, but things happen. Lots of rainwater. We go and stare at the rain all the time. All right, so for part A, how many cubic feet of rainwater? I feel like that should be how much. But anyways, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 is less than or equal to t is less than or equal to 8? So we just want to know how much rainwater goes into the pipe. I'm not concerned about water draining out. I'm not concerned about the amount of water that is there to begin with. I just want to know how much water goes in. So I have an equation for the rate of water going in. So if I want to find the amount, I'm going to integrate backwards to find that total amount that goes in. So for part A, we want to find, go away. For part A, I want to find the integral from 0 to 8 of, I believe it's R of t, right? Yeah, R of t. And when you're writing for your exam, you can be that lazy. You don't have to write out R of t all the way. You can just abbreviate and say R of t. So the integral from 0 to 8 of R of t dt, 20 sine of t squared over 35. So math, option 9 for that function integral, 0 to 8. 8. And then it's 20, I believe. Yep. 20 sine alpha y equals, first option for that fraction, t squared over 35. Close parentheses. And then dx. Now, as always, it's a pragmatic moment to make sure you check on your calculator that you're in radians mode. I am. Everything for the calculator exam will be in radians mode. Hit enter. We get 76.570. It doesn't tell us to round to a whole number. Nope. So we are good. As always, I just like to check to make sure we're good. Yep, 76.570. All right. And then units, cubic feet, so feet cubed. Remember, we always want to talk about units when they include them in the problem. You never know when they're going to take off a point for no units. All right, B is the amount of water in the pipe increasing or decreasing at time t equals 3 hours. And give a reason for your answer. All right, so is the amount of water in the pipe increasing or decreasing at time t equals 3? So the amount of the water in the pipe is going to be dependent on two things. It's going to be dependent on R of t, rainwater flowing in, and it's going to be dependent on D of t, rainwater flowing out. I'm also talking about the exact amount, so I am going to include that 30 cubic feet of water in the pipe at time t equals 0. So for part B, this is going to be the first time of our mega equation for this one. So 30 plus the integral from 0 to t of R of t minus D of t dt. So that r of t minus d of t, that's rainwater going in minus rainwater that's draining. Then I want to know if this equation, this amount of water is increasing or decreasing. So if I want to know about increasing or decreasing, what am I going to do? I'm going to go to the first derivative. So I need to derive this equation. So the derivative of this would be 30 is going to go away. Derivative of the integral is just the original function. So r of t minus d of t. Okay, so that's our first derivative. Now, I want to find if this derivative is positive or negative, because if it's positive, it's going to be increasing the amount of water. If it is negative, it's going to be decreasing. And I just want to find it specifically at t equals 3. I'm not trying to find intervals or anything yet. I'm just trying to find it at t equals 3. So, r of 3 minus d of 3 equals. So I'm going to plug both these equations into my calculator. So 20 sine alpha y equals, believe it's t squared, yep. So 3 squared over 35 minus, and then it's negative 0.04 t cubed plus 0.4 and then 0.96 squared plus 0.96 is 3. It's that big old mess. So we get negative 0.314. Okay, so since r of 3 minus d of 3 is negative, that means we are going to be decreasing the amount of water. So r of 3 minus d of 3 is less than 0. Therefore, the amount of water in the pipe is decreasing at t equals 3. Okay, so once again, using our calculus house, talking about increasing, decreasing. One of the things you probably started to notice with these is, contrary to when we did our chapter 4 test, you're not really going to get questions where it's just calc house all the way through. They're just going to kind of stick it in parts. So you always kind of need to be ready to be able to bust it out. All right, part C. At what time t from 0 to 8 is the amount of water in the pipe at a minimum? Justify your answer. It doesn't specify absolute minimum, but I mean, they're basically asking the absolute minimum. Sometimes they're going to leave out absolute, but essentially, we're going to find any relative maxes or mins, only caring about the mins, obviously, and then we're also going to compare the endpoints. So for part C, we're talking about the amount of water in the pipe, so we're using that big equation for part C. So 30 plus the integral from 0 to t of r of t dt. It's not that big mess. All right, and then we want to find this. We're trying to find when the derivative is equal to 0, because I want to find any relative maxes or mins. So once again, we take the derivative, which is just that r of t minus d of t. Then I'm going to set that equal to 0. And I'm going to go search for any of those maxes or mins. Now, a lot of y'all have been asking how to do this in the calculator. So go to your y equals. We're going to put both of these equations in. So 20 sine of t squared over 35 minus, make sure I put everything in parentheses, so 0.04 x to the third plus 0.4x squared plus 0.96x. And the other one I'm going to put in 0. So y1 I put the r of t minus d of t. y2 I'm putting in 0. We go to our graph. It's probably going to be a mess. Oh, it might not be too terrible. Oh, what did I mess up? All right, so I figured out what I did wrong. I forgot the negative in front of the 0.04. So calculator / trying to read and make a video at the same time error. But now we add that negative. We go to our graph. Still kind of like not the greatest in the world, so we can adjust the window a bit. I don't really care about anything except 0 to 8, but I'm going to go just a little bit bigger to make sure that I can see everything. Y min and Y max is probably fine. All right. And I don't care about that one either, so I am just going to take out that last bit there. So I can just see really 0 to 8. There we go. Okay, so we can clearly see there's one right here at the beginning, which that's good to know. One of our endpoints is actually a relative max or relative min. And then we have one here in the middle. So second, calculate, option 5, intersect. Then I'm going to arrow on over to that intersection point, hit enter 1, 2, 3 times, and it'll give me that intersection point, 3.27165. Okay, so now I'm going to find, if you've noticed on the scoring reports, they like to make a little table, which tables are kind of cool. So t value of 0, 3.27165, and 8, and I'm going to find all of these values. Now, remember, I'm just plugging t in here for length of the video's sake. I'm just going to pull those values real quick. So 30, 27.964, and 8. Oh, sorry. At 8, 48.543. All right. And the question actually asked us, at what time is the amount of water in the pipe at a minimum? So out of these three, 27.964 is the least. So we'd say the water is at a minimum at t equals 3.271 as in hours. Doesn't really matter when you're just talking about it like this, but doesn't hurt to include it. 3.271 hours, because we could say the value is less than value at t equals 0 and t equals 8. You might notice that was probably not my greatest written out answer ever, but once again, once you've shown all this work that's here, you're really just summing up that, like, hey, I found my work up here, so it's less than those other numbers. Those other numbers, that's the work, so take it or leave it. All right, part D. The pipe can hold 50 cubic feet of water before overflowing for t is greater than 8. Water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow, right? But do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so this question kind of reads a little bit confusing, but it's really not easy. It's not hard. It's like the easiest last little step you could ever think of. So all I want to show is, when is the amount of water in the pipe going to be greater than 50 cubic feet? At some point, the R of t is going to be greater than d of t for so long that there's going to be more water in the pipe. So all I need to show is when is this equation, the equation we got in part C, this equation, when is that equation going to be greater than 50? Well, all I need to do is take that equation and set it equal to 50, so I can prove that. So for part D, I just want to say 30 plus the integral from 0, but instead of t, I'm going to say w, because that's what they tell us to use. Time w when the pipe will begin to overflow. R of t minus d of t. And I'm going to set that equal to 50, as if I was going to solve this for that variable w. What would w actually equal? And then you're done. Nice and easy, because it just tells you to set up an equation, not to actually solve anything. So we are all good to go. All right. That concludes your walkthrough for last week's FRQs. Sorry it's so late, but stuff happens.